My name is Samuel Myron, and I am a post-baccalaureate intern in the Statistical Sciences Group. I am presenting the work titled In-situ Inference for Exascale Computing, which is a component of a larger LDRD project. The motivation for this project is that complex simulations run on high-performance computers produce more data than can be saved for offline analysis. This means that we are limited to analyzing only a small fraction of the data produced by valuable simulations. You might think, if we want to access the data, why don't we perform the data analysis as part of the simulation while it runs? This is exactly what we are proposing, but implementing this idea is challenging, first because these simulations are often distributed across many different nodes within the computing system, and secondly, because these simulations are written in languages that are hard to use for rapid data science prototyping like Fortran. To address these challenges, our project is developing both the computer science and the statistical tools to allow analysis on all of the simulation data in situ. First, I'd like to describe the issue with data storage and data transfer a bit further. As high-performance computing systems are reaching exascale capabilities, that is 10 to the 18 operations per second, our ability to store these computations and transfer this data is advancing at a much slower rate. So while our simulations may be able to run with a total of 125 petabytes per second, with an on-node computational capability of 4.5 petabytes per second, we're only able to transfer a fraction of this data between nodes at 24 terabytes per second. So our inter-node communication abilities are constrained by data transfer rates. This is important when performing statistical analysis and information needs to be transferred between nodes. Additionally, our pipeline is constrained even further as we attempt to transmit data from the HPC system to an offline database. Ultimately, we are left with 0.001% of the information we'd like to analyze. So we are proposing to access all of this data by performing the analysis while the simulation runs. I am focusing on the statistical tool that will help in this analysis, the Gaussian process model. A Gaussian process is a statistical modeling technique that we will fit to the data being produced while the simulation runs. It is a model that represents the data, which is important because the model acts as a lower dimensional representation of this data, which allows us to perform a variety of analyses on the smaller model instead of on the larger data set itself. However, since Gaussian processes scale poorly as the number of data points increases, we use sparse variational Gaussian processes instead. In this type of model, instead of fitting the model to every single data point, which is quite cumbersome, we fit to a small number of data points called inducing points, whose values and locations are optimized to provide the best model. It is up to the user to define how many inducing points they want. So in the figure, if our simulation data is in blue, we can approximate that data using the inducing points in red, and fit our model to those points rather than to all of the blue points. In this case, there are 10 inducing points, but we could have chosen 2 or 50. But if you had only chosen 2, your model would be very rigid and wouldn't have all of the curvatures that you need to represent. And if you chose 50, your model is getting closer and closer to the number of data points available, so you face the scaling issue once again. Therefore, we are looking for the sweet spot between model complexity and predictive capability. To understand why we want to find this sweet spot, it is helpful to take a look at some real data from a real simulation. Shown in the top left figure is about 46,000 points that describe a predicted temperature for various combinations of latitude and longitude. This data comes from the Energy Exascale Earth System model, which predicts more than just temperature, like pressures and wind velocities. However, the complete picture shown in the top left figure was formed by stitching together data from many different nodes. Because what really happens is that within the high-performance computing system, the simulation is effectively distributed across many nodes. For example, the part of the simulation responsible for predicting the temperature throughout Indiana is likely a different node from the one that predicts for Ohio. We try to represent this partitioning of the simulation by splitting the data up into 100 tiles, because what we will eventually do is fit a Gaussian process model locally on each node. Then we'll transmit the details of the models to other nodes such that we can get a global fit of all of the data. The key thing here is that transferring data between nodes is expensive, so we want to be careful about how much data we transmit. And as you remember, we get to choose how large our model is by choosing the number of inducing points. So if we choose more inducing points, we get a better fit of the model, and if we choose fewer, we don't have to transmit as much data. So this is the motivation behind my project, trying to find 1, the minimum number of inducing points we need to represent the data adequately, and 2, to determine this number before we fit any model. With the aim of answering these research goals, we need to determine how many inducing points are needed to describe the data adequately. To do this, I begin by selecting a single partition from the figure in the top left. In this case, it happens to be the Pacific coast of the United States. I then fit multiple Gaussian process models to the data contained within this partition, but I varied the number of inducing points for each model. You can see in the top right figure how there are 7 tiles. What is shown is the original data in the background with the final locations of the inducing points outlined in black. So in the first tile, there are 3 inducing points, in the second there are 6, and so on up to 25 points. These plots simply demonstrate how the final optimized locations of the inducing points depends on how many there are. Regardless of where the final locations are, once the models are optimized, we can then evaluate how well the model represents the data by calculating the root mean square error, or RMSE, between the original data and the model's prediction of the data. Then we plot the RMSE as a function of the number of inducing points to see how models perform with larger numbers compared to those with fewer numbers. Overall, we see in these types of plots a decreasing trend, which is what we would expect, because more complex models are expected to perform better. With this approach in hand, we then perform this analysis for all 100 partitions. We take each partition, fit multiple models, and evaluate the model performance. You can see that in the background of this slide, how each partition has its original data, and then a model predictive capability curve in green plotted above it. This helps us visually see which partitions may be more difficult to fit so that we can search for a metric of the original data that can point to how many inducing points we might need. The general school of thought is that if one partition's data is more complicated or more varied than another's, then we will need to use more inducing points for that partition. Therefore, we compute metrics like variance, range, and standard deviation of the original data. Then we look at every green RMSE curve and we choose a preferred number of inducing points that we feel strikes a balance between model complexity and predictive capability. Once we do this analysis for all partitions, we plot the information and look for trends. What we expected to see is that as variance increases, the preferred number of inducing points would also increase by some clear functional relationship. This is what I have plotted on the red line. However, what we actually see is little to no trend at all between the preferred number of inducing points and whatever summary statistic we used. While I have a few reasons for why we get unexpected results here, that discussion is beyond the scope of this presentation. While the results we reached are not necessarily what we expected, they are results nonetheless. Our first research goal was to determine the minimum number of inducing points needed for a given set of data. What we found is that relatively small numbers of inducing points is, for the most part, good enough. This number ranges between 2 and 6 inducing points, which is still sufficiently small enough to effectively transfer the model data across nodes. The second goal was to determine the number based on the raw data. We learned that a trend for this may not exist and that a hand-tailored approach for each simulation may be necessary. As a bonus result, in the process of answering these research goals, we ran the programming software that fits these models hundreds of thousands of times. Since this software is being developed in-house in real time, running the code this many times and across so many different regimes has proven to be an invaluable debugging and validation step. With high-performance computing reaching exascale capabilities within the next decade, our ability to analyze all of the data produced from simulations is crucial for maintaining the nuclear stockpile and for scientific pursuits generally. My work is developing the statistical analysis tools so that we can perform the data analysis in situ, as opposed to having to perform the analysis on only 1,000th of a percent of the data offline.